Hey everyone, so I'm Sean, and this is my presentation for the computer vision final project. Today we're going to talk about bug detection and recognition using GraphCut and DA2 with ResNet 18. So my initial plan was to develop a belt car that would patrols around a greenhouse, and whenever it detects a bug on the plants, it would do some certain actions to remove the bug from the plants, like spraying pesticides, blowing airs, and so on. However, that is a lot of work. So for this final project, I explored around like how to train a model that could easily detect and identify type of bugs with the limited amount of image data sets. Uh, just a brief summary before we begin. I'll try to use segmentation algorithm called GraphCut and depth anything network to get the box region in the image. And I trained a modified ResNet 18 for a classification. I'll evaluate performance of my system with two factors. First, how many bugs are detected in all images. And second, what's the classification accuracy. So we will talk about some previous work that's related to our analysis. First is GraphCut. It was originally developed in 2004 by Ruther C, and it is essentially an image segmentation method based on graph cuts. Initially, we have to specify bounding box around the object to be segmented. Then in each iteration, um, outside of the bounding box, that would be the background, and inside of the bounding box would be the foreground. So in each iteration, we'll use Gaussian mixture model to estimate foreground and background color distribution. Then we will apply GraphCut optimization to separate the object from the background. Um, and with this, we will get a binary image as a result. So in my case, I have a bounding box with half the size of the image in the center, because 99% of the images in the datasets have the box in the center. However, for real life scenarios, we have to figure out other ways to initialize the bounding box. Um, well, DA2 is another pre-trained deep network we have seen using in the past projects. The network will find the depth of each pixel in the image. We can utilize this to threshold and get a binary image. Next, the question is, how do we utilize these two methods together? Well, first of all, we can use bitwise or bitwise AND operation on both binary images coming from GraphCut and DA2. Or we can just use the binary image coming from GraphCut itself. An AND operation would produce a tighter bounding box and a stricter rule of detecting the object as both pixels from GraphCut and DA2 has to be 1 in order for the result to be 1. And conversely, OR operation would make a looser result with a larger bounding box. So GraphCut itself would get us a moderate looking bounding box. And here's a few examples. We can see the worm coming from the GraphCut algorithm. We can correctly identify them and find the region where the worm is located. And for the second example, we can see a spider coming from the binary image from DA2 network and the binary image from the GraphCut network, and we use the OR operation to combine them together to find the final binary image. And then we have another worm, which we have a binary image from the GraphCut algorithm and a binary image from the DA2 network, and we use AND operation to combine both the image, and we can successfully find the actual position of the worm. Next, let's look at the previous work on how to identify tracks of concrete with ResNet 18 and with a very limited amount of data. So in this previous work, the authors explored the best way to train a CNN model with different training configuration variables such as different learning rates, different epochs, or they change the image resolution. Like what we can see here, if you have a 64 resolution, you will get the lower accuracy, lower testing accuracy. But if you increase the resolution to 256, you will get a higher accuracy after more iterations. And it also mentions some training technique like adjusting the brightness, um, which can greatly affect the learning accuracy. And on the top right, you can see a table of the result of training with different brightness of the image data, and a table of loss function on different. Oh yeah, I've already mentioned this. And there's also a result of detection and recognition on the bottom left. Then let's talk about our ResNet 18. So it is a lightweight and efficient classification model as we study for assessment 3 in past. By learning the residual with skip connections, we avoid the problem of vanishing and exploding or exploding gradients. So the only architecture I modify here is the last layer. I replace it with a 512 to 9 fully connected layers to match the number of labels of our datasets. Next, we talk about the training and the testing plan. So initially, GrabCAD and DA2 and finding the regions are done in C++. It would be like the cropped regions would be saved as in individual file, and then the C++ side would send the file path to a Python flag server for the classification results. A model is trained and tested in Python initially, and once it is trained and ready, we'll host a flag server that would take requests and read the image path for classification and return it the label to the clients. So once the C++ side receives the classification, it will label each regions with the bounding box and save the label image as a new file. Lastly, we'll look at my training results from each combination of segmentation methods. So the goal of training is to find a model that produces the optimal testing accuracy. So for this, the box region generated by bitwise OR operation, we have a total of 660 box detected in 578 images. We will see a table in the previous slides. I believe most of the bounding boxes are too large and they do not strictly go around the box. So model's accuracy cannot surpass around like 70% after multiple epochs. However, in most cases, it can still correctly label these regions, like we can see here, a grasshopper being correctly labeled with the bounding box. But for this mites, you can see the bounding box that even include the background plants as well. So I think that is what caused the lower accuracy for this training and testing. Next, we will see a box regions generated by bitwise AND operation. Since there's a stricter rule, we have less bugs detected. We have a total of 120 bugs detected in 578 images. And since there is so much less regions, the testing accuracy also didn't go above 70% after double the amount of epochs. And we can see a worm here that can be visually detected, but it is not detected by our system. But on the left, we see a bullworm that has a tight bounding box around them and correctly labeled. And here we can see some tables for our loss function for both training and evaluation loss. And lastly, we will look at box region generated by GrabCAD only. And there's a total of 337 box regions found in 578 images. This is for the training data sets. And since regions and bounding boxes are pretty moderate, with only 30 epochs, and we can reach a testing accuracy of 93.8%, which is pretty decent. The image on the right shows a mite being correctly labeled with the bounding box. And one thing to notice here is that after 100 epochs, we didn't get a better accuracy um, than 93.8%, which means the accuracy is saturated around like 93.8%. We're gonna look at the demo for this whole project. Um, so we're just going to loop through every single testing file and pass each frame into this grabcut algorithm function and get the binary file. And for each binary file, it has to go through the dilation and erosion, and by this OpenCV function called connected component with stats, we'll find regions. And for each region that is greater than 3000, um, we will put the bounding box around them and save the cropped region as a new file. And by sending the path of the new cropped file to the Python server, we will get the label return, and we will put the label onto the bounding box as well. Next, we're gonna look at the server part. So it is right here. It is essentially a flag server with only one endpoint, predict, and initially just gonna parse the path and pass it into the model that we trained previously, and then return the label as a result to the clients. So here we're just gonna get the server up and running. So now it is running. We're gonna come back to the C++ side. I've already compiled the binary for this program. So it is just going to loop through each image and find the detected bugs. Here we're just gonna look at the random file. So this is a ball worm, and it is being correctly parsed and detected. So yeah, thank you very much for listening.